Hello everyone. So in this video we'll be talking about linear regression and how you can use a simple linear model to relate or model the relationship between two variables x and y. So let's get started. So the linear regression model is very familiar. It's just basically a straight line. So we'll model the relationship between an explanatory variable, which we'll write as x, and a response variable, which we'll call y, as the following. yi, or the response variable for subject or observation I, will just be our y-intercept, beta 0, plus beta 1 times the explanatory variable x, plus some extra error term, which we'll denote as epsilon. Now, given a data set, we will fit the linear regression model, so we'll come up with estimated values for beta 0 and beta 1, our intercept and our slope parameters, plus some extra our predicted value then, y. So y hat becomes the predicted value of the response variable for a given value or level of the explanatory variable. Beta hat 0 is the predicted value of the response variable when the explanatory variable is 0. And then beta 1 is the estimated change in the response variable from a 1 unit change in the explanatory variable. So we'll use a data set called the brain empathy data set to get some practice with linear regression. This comes from kind of a fun study that was done using 16 heterosexual couples in their mid-20s. They picked couples that had been in a long-term relationship for this experiment. So they were either married or had been dating for at least 2 years. In this experiment, the male partner's hand was zapped with an electrode while the female partner watched. As she watched, they measured the activity in several parts of her brain that would respond to her own pain. The idea was that if the female partner is feeling empathetic, then these areas of her brain would light up when watching someone that she cared about feeling the pain. This brain activity was then recorded as a fraction of the activity observed when the woman herself was zapped with the electrode. So a brain activity of 0.5 means that she had half the electrical signal when her partner was shocked as she did when she herself was shocked. The women also completed a psychological test designed to measure a person's empathy levels. So is this test a good predictor for the brain reactions to the partner's brain? So the response variable here, or the y variable, the variable we care most about is the physical reaction to the partner's pain. We think that we could use that empathy score to predict it. So our model looks like this. Y is equal to beta 0 plus beta 1 times x. You can write this in terms of x and y, or if you prefer, in terms of the actual variables. So we think that the brain activity level is a linear function of the empathy score. Either one is acceptable. So before we actually fit this linear model, let's take a look at the data and make sure it's appropriate. There are a few things that need to be satisfied. So we need to have a linear relationship between our variables, and we also want these variables to be numeric. They need to make sense in a linear function. So our explanatory variable, the empathy column, is numeric. Brain activity is numeric, so we're good there. Let's look at the correlation. So the correlation between a person's empathy score and their brain activity is 0.51, roughly. So there is some correlation. It's certainly not a very strong correlation, however, between empathy and brain activity. Now, correlation doesn't tell us everything. Let's look at an actual plot of this data. So we can produce a plot using the geom point option to draw the scatter plot. Here, this new highlighted option, geom smooth, adds a smooth trend line using a linear model. So method equals LM says to use a linear model. Writing SE equals false prevents drawing what are called standard error ranges. So essentially, we just want to see the line. We don't want to see anything surrounding that line. So here's what this model looks like. In general, as empathy is increasing, So is brain activity. We do have a linear trend. There's some variability here. Points fall above the line, points fall below the line. There's also an outlier. There's also someone with an extremely high empathy score compared to the rest of the observations. So this outlier may cause us some problems later on. So to get the fitted linear regression model, we can use the LM function in R. LM stands for linear model. So we'll see how brain activity depends on empathy level. So this tilde you can read as depends, essentially. Our data set is the brain empathy data set. So we get two values out. We get an estimate for the intercept, and we get an estimate for the slope. So our fitted regression model looks like this. Y hat I is equal to negative 0.007254 plus 0.006938 times x. One word to point out at this stage is that the magnitude of these coefficients doesn't really tell us anything about how strong the relationship is. These completely depend on the units of the original data. So we may have large slopes, we may have small slopes. The units of x definitely matter here. So for any value of x, we can either predict or estimate y using this fitted linear model. The way we do that is to take this x and just plug it in to the equation that we've generated. So we have a new couple who's coming to participate in this experiment. The female partner scores an 82 on the empathy assessment. Let's predict her brain response to those shocks. So our prediction would be found by taking this value of 82 and plugging it in for our x. So our prediction is y hat is negative 0.007 plus 0.0069 times 82, or 0.56. So we predict that she'll show about 56% of the brain activity as she did when she herself was shocked. We may be off a little bit with our predictions, and the amount that we are off we refer to as our residuals. So the residuals are just the difference between the predicted value and the observed value. Another word for these are the errors. So how wrong were we? We calculate these errors, which we'll denote with an E standing for error, as y hat minus y. So we'll take our predicted value, subtract our observed value. So let's look at subject 2 in this data set. Subject 2 has an empathy assessment score of 53 and a brain response of 0.392. So let's predict her response to the shocks that her male partner is receiving. We'll do the prediction first, so we'll plug in 53 to our linear model. My predicted value then is 0.36. We predict that she'll feel about 36% of the activity. Her residual then is the difference between her predicted value and her observed value, so we get negative 0.03. For this subject, we underpredicted. Her actual brain response of 0.392 was a little bit higher than what we predicted, so we get a negative residual. We'll get a negative residual if we have underpredicted in our model. We'll get a positive residual if we've overpredicted. So I'd like you to try this one on your own. Subject 3 is a little bit of an anomaly. So subject 3 has an empathy assessment score of 41 and a very low brain response. Subject 3's response is only 0.005. So you should get, when you do this calculation, the predicted value y hat here, the error y hat here, the error E. Notice how large that error is. Certainly much larger than the previous error, and because it's positive, we know that we've overestimated pretty dramatically. Now, when we fit this linear model, we do so using a technique called least squares regression. And here's how least squares regression works. We've got two conditions or two constraints that we'll use to calculate this line. first constraint is that the residuals must sum to 0. In other words, we want those errors that we're off by to average out to about 0. Second condition is that we want the squared residuals to be minimized. We want those to be as small as they can possibly be. For a good visual explanation, if you're a visual learner, I highly recommend this website linked here at setosa.io. There are some great animations for how this all works mathematically. Now, there are some conditions, like there are with every statistical model. The conditions for a linear regression model follow sort of this nice line abbreviation. So to use a linear model, we must have those line conditions met. The 4 line conditions are the following. So x and y must have a linear relationship. We don't want to use this model to describe data that is not linearly related. Second assumption is that the individual observations or residuals should be independent. So there should be no connection between the residuals for subject 1 compared to subject 2 compared to subject 3. All of those should be unrelated. If we have a random sample, then this independence condition is usually satisfied pretty easily. Third condition, the residuals should be normally distributed with mean 0. So we want those residuals to average out to 0. Further, we want them to follow a normal distribution. And then finally, the errors need to have constant variance. We want them to have about the same variability no matter what the value of x is. So let's take a look at this data and see how well this linear model seems to fit. The trend line, or the blue line, fits through the data pretty well. There are definitely some areas where the points are above the line, definitely some areas where the points are below the line. This outlier here may also be a bit of a concern because the line is very close to that outlier. Maybe that outlier is really having a lot of power over the model. So to find out a bit more information about our linear regression model, besides just the estimated slope and intercept, we can save our model into a new object. Here I've just called this model. And we can use the summary function to find out more information about this model. Now there's 3 major tables that come out of this: a residual table, a coefficient table, and then some model diagnostic information. Let's talk about how to interpret each of these. So this is how the residuals are distributed. We're assuming when we do this model fitting that the residuals are normally distributed. Now if the residuals are normally distributed with mean 0, because that normal distribution is symmetric, the median or the midpoint should also be 0. So we want this residual number to be close to 0. It doesn't have to be perfectly at 0, but it should be close. We also want to take advantage of the fact that the model is symmetric. So because it's symmetric, the first quartile and the third quartile should have roughly the same absolute value. So that's what we'll look for to help us determine, or one technique that we can use to help us determine whether the residuals are normally distributed. The next table that we'll look at are the coefficients. The first column, the estimate column, gives us those estimated coefficients. We also get some more information. We get a standard error of those, we get a t-score, and we get a p-value. These p-values can help us determine whether or not our model is, quote, significant, or whether or not there's a strong relationship between x and y. Even though there's 2 p-values reported here, we're really going to focus on the empathy p-value, and here's why. That p-value column is actually showing you the results of 2 hypothesis tests, not just one. The first hypothesis test is testing whether or not the y-intercept term, the beta, is equal to 0. So if beta is equal to 0, then the predicted value of y when x is equal to 0 would be 0. Does that tell us whether or not x and y are related? Not really. It just tells us where the model crosses that y-intercept. Now here's the second hypothesis test. This one's more interesting. This is testing whether or not the slope is equal to 0. So if the slope were equal to 0, what would that look like? Well, our data would essentially be following a horizontal line. There would be no trend. So if the slope is equal to 0, that does tell us that x and y aren't actually related. But if we can reject that hypothesis and conclude that the slope is something different from 0, then x and y are related. So in order to evaluate the conditions of our model, we can use some plots of the residuals, or residual plots, to help us out. You can generate these using a function called plot. So we can just plot our model. You'll get 4 plots when you run this. We only really care about the first 2. So the first plot uses a scatter plot of the residuals against the fitted line. What this evaluates is constant variance and independent residuals. So what you want to see in this plot is random variation above and below 0 with no clear pattern. So here is what the first residual plot looks like for this data. We have our residuals marked with circles. 0 is a gray dotted line. Red is a trend line applied to this. Overall, there's no major pattern with these residuals. They look pretty independent. They're all kind of scattered randomly around that line of 0. There might be one problem, though. There might be a problem with non-constant variance looking at this plot. The points are a lot more spread out here than they are here and here. Now, of course, how much of that is due to this being a small sample size, we really can't say. The second residual plot uses a normal QQ plot to help us see whether the residuals are normally distributed. This is going to look a little different than the previous QQ plot, but the interpretation is the same. We want to see most dots near the diagonal line. So here's the QQ plot. Again, most of these residuals fall pretty close to the straight line. So I'm not overly concerned about whether or not my residuals are normally distributed. They appear to be pretty close to a normal. Now, something else that I'll want to evaluate when I'm looking at this model is whether or not there are any major outliers. So outliers are data points that stand out. These can be pretty far away from the pattern of the rest of the data, either far below the pattern or far above the pattern. The reason we're worried about these is that outliers can have a strong effect on the linear regression model. So one thing we can do is calculate a standardized residual, or essentially a z-score for a residual. We'll take each error for each residual, subtract the mean, divide by the standard deviation. Now, what R will do automatically in these residual plots is number or write the observation number of these observations with the highest standardized residuals. So observation 5, 7, and 10 have the highest standardized residuals. They might be ones that we'll be concerned about. We might also look for influential outliers. So are there outliers present that might tilt that regression line, bring that regression line close to them? So the observations that we've identified as potential outliers are 5, 7, and 10. Let's look at these in the data. I'm using a new plot geometry for us here called geom_label. For each point, I'm labeling it with the row name, which is just simply the observation number. So observations 5 and 7 are down here below the line, still following the trend of the data, so I'm not too concerned about that. Observation 10 is up here, still following the trend of the data, so I'm not too concerned about that one either. The one that is potentially influential is observation 16. This is pretty far from the rest of the data, and it looks like maybe the regression line has been somewhat tilted toward it. Now, there's one other thing that I tend to be concerned about when I'm looking at a linear regression model, specifically making predictions from a linear regression model, and that's the idea of extrapolation. What we want to do is make sure that we're not using this regression line to predict beyond the range of our observed data. So what is going to happen then if we have a subject whose empathy score is, say, 0? How does that affect things? Well, we'll predict a brain activity score plugging 0 into x of negative 0.007. That's the problem. The reason that's a problem is because the brain activity score is a percent of activity when this person was actually being shocked themselves. Can't really have a negative percent of brain activity. So we're getting a prediction that doesn't make sense when we're extrapolating. When we're extrapolating, we're predicting that the pattern in the data won't change. This is a pretty big assumption. So to avoid extrapolation, make sure you're only predicting for values within the range of observed data or close to the range of our observed data. Finally, let's talk about how much the model is explaining. So if we want to know how much variation in our data can be explained using our model, we can use something like this, multiple r squared, or the coefficient of determination. So the coefficient of determination represents the proportion of variation in the response variable that can be explained with the linear model. So for us, we're explaining about 26% of the changes in brain activity just using this empathy score. Now, R refers to this coefficient of determination as r squared, and there's kind of a fun reason for why this is happening. We used the letter R to represent the correlation previously. Now, the correlation between empathy and brain activity is 0.5086. If I take that correlation, or that R, and square it, I get the coefficient of determination back. So R squared, the coefficient of determination, is truly r squared. So once you know correlation, you can get this coefficient of determination, or vice versa. You can take this coefficient of determination and use it to find the correlation. So we'll stop here with our introduction to linear regression. In next week's video, we'll cover our final topic for this semester, which is multiple regression. Have a great day.